Well, welcome back to another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs here with Lyft. Appreciate everyone taking the time to join us today and learn a little bit more about custom alloys and composites by our friends at Loukus Technologies. Certainly appreciate their membership and their partnership with us, and excited to hear about what they are going to talk about today. Our friend Adam Loukus. Name may sound familiar because I just said Loukus Technologies. So your name's on the building, brother. All right. So hey, thank you very much for joining us today. I do have a few housekeeping items to take care of before we get the ball rolling. Everyone should be on mute. If you are not, please go ahead and do so. We are recording this session, so I want to reduce as much background noise as we can and make sure that folks can hear the presentation. We will be posting this recording on our website at lift.technology a little bit later. So you can please go ahead and check back if there's something that caught your interest, or you want to revisit, or you want to go ahead and send it to folks who are unable to join for one reason or another. We will also be having a Q&A session after the presentation, but don't let that stop you from asking questions during the presentation. Go ahead and use the Q&A function, please, that is in the on the Zoom toolbar that we're all very familiar with these days. You can go ahead and avoid the chat function. Use the Q&A function. That makes life easier for the Q&A. So please fire those questions off to Adam, and we will facilitate that a little bit later. I will take those questions, and Adam and I will have a little conversation around those questions later. So with that housekeeping, I do want to take a couple of minutes and share a little bit about Lyft, who we are, what we do, for those who do not know. Lyft is a nonprofit, public-private partnership, Department of Defense National Manufacturing Innovation Institute. So what does that mean? That means we are driving American manufacturing into the future through technology and talent development. We know that our country's national economy, our economic resiliency, our national security, all rests on the advanced manufacturing sector. We want to make sure that the next leader around the world, the next is the U.S. in advanced manufacturing, that we maintain our stature there, because if someone else tackles advanced manufacturing first, they're going to go ahead and take the lead, and we do not want that to happen as a DoD Manufacturing Innovation Institute. We want to make sure that what the country needs, what the warfighter needs, are made here in this nation. So what do we tackle here at Lyft? At Lyft, we work at the intersection of material science, manufacturing process, and systems engineering, along with talent development. So we want to make sure that we know what we need to make in the future. So how do we make them, and what do we make it out of? That's what we are working on with our partners like Loukus Technologies and our ecosystem around the country. Want to make sure that we know what we're making it out of. How do we make it? Make sure it's fit for purpose at the end of the day, and make sure that we have the talent ready to work with these new technologies when they hit the shop floor. So we have two programs that we operate here at Lyft: Leading Innovations for Tomorrow, which is our technology program, and Learning Innovations for Tomorrow, which is our talent program. I'll touch a little bit on the technology program first. Leading Innovations for Tomorrow. All of our projects and programs in some way, shape, or form revolve around these four pillars of technology. A little bit deeper dive here, all the way from ICME, integrated computational materials engineering, which is where we're modeling and simulating these materials and manufacturing processes on the virtual side, and then taking them into the physical world with advanced alloy and process development. See some of the things we're working on with lightweight armor development and rare earth materials and hypersonics materials development. Then, as we're developing and working with these new materials, how do we join them together? Are there new ways we need to work on there? As we develop these materials, can we model the joining in a way that we know what we're doing when we need to join them, and they're, again, fit for purpose? And then finally, agile and smarter manufacturing. Are there new ways of doing things? Can we be more nimble as it relates to some of these processes, like additive manufacturing? Can we metal additive? Can we use wire arc for that? Can we use cold spray technology? Can we use incremental sheet forming to form parts and pieces out of sheet metals? All of that is happening throughout our ecosystem and here at our Detroit headquarters. A little bit about on the Learning Innovation for Tomorrow, our talent program. This is all, again, still about innovation and new ways of doing things, but now we're talking about new learning tools, new pathways, new venues. And that really starts with our Lift Learning Lab, which is here at our Detroit facility, perched above our high bay. It's our pilot plant, if you will, for new curriculum, new ways of teaching students advanced manufacturing in 2022. Bring students in here, bring teachers in here, bring industry here, learning what we need to know to help educate those manufacturers of the future. So that turned into our Ignite Mastering Manufacturing curriculum, which is our high school curriculum, which is a 3-year program. It's available around, it's in about 13, 14 states now, about 3,500 students each day participating in that. Everything they need to know about to expose themselves to advanced manufacturing, material science, electronics, pneumatics, smarter manufacturing, those kinds of things, really wetting their whistle as it relates to advanced manufacturing and providing a pathway for them to either enter the workforce or continue their education afterwards. We also provide some opportunities for our adult learners, folks who may be looking for a new skill, upskill in some of the most in-demand jobs that are available today. CNC, machining, welding, industrial technology, maintenance, robotics, all of those are available. We work with National Institute of Metalworking Skills curriculum, American Welding Society curriculum, SACA on the robotics side, nationally portable, industry recognized credentials that are mostly free of charge for our students here to get those credentials and become part of the advanced manufacturing workforce. Those programs are also available in Operation Next, which is a program that we are super proud of here at Lift. It is available to separating service members 6 months before they leave the service if they're active duty, or Guard and Reserve members and their spouses. Some of those folks are underemployed, unemployed, maybe looking for a new skill. So we provide that as well, around 13 or 14 locations around the country, super close to our hearts as a Department of Defense Manufacturing Innovation Institute. Did mention that we are a membership-based organization. Loukus Technology is certainly one of those members, and we're very happy to have them on board. So we may have some other members on the call here today as well, but on the screen here is what you see is our value proposition. What do we provide our members? We are a trusted advisor. We're not selling a particular product or service. We're trying to advance technologies from commercialization, or from concept to commercialization, and we have experts in-house and across our ecosystem help you do just that. And that takes us to the technology accelerator side. We are, not selling a product or service. We're selling our expertise, our ecosystem's expertise to move the needle in advanced manufacturing and advance these concepts moving forward so they can be utilized faster by industry and for the warfighter. A technology showcase. If you have not been to our Detroit facility, I encourage you to do so. Not only are we showing the art of the possible, what the future of advanced manufacturing looks like, but it is a sandbox where we are working on these technologies each and every day. We're a connector and a convener. Thank you so much for joining us today. This is part of that connecting and convening. So little did you know you were a part of that value proposition just by signing up for this webinar. We are a talent developer. We talked about some of that already, providing opportunities for high school students. We have a lot of college students working on on some of our technology programs, and our adult learners give them opportunities for certification. And finally, we are a government partner. The federal government can be an unwieldy place, a bureaucratic place, a challenging place to start working with, particularly for our small to medium-sized manufacturers and members. So we provide that conduit to make accessing that a little bit easier and to try to help move those innovations into the DoD as quickly as possible. So you're not come here to hear from me, but I want to thank you for indulging me, give you a little bit of information about Lift. I encourage you to follow us on our social channels, give us a phone call, shoot us an email, visit our website to learn a little bit more about membership and how we might be able to help you take your innovations forward. But with that, I'm going to turn the program over to Adam Loukus of Loukus Technologies to talk to us about advances in manufacturing custom alloys and composites. So I'm going to stop sharing my screen and turn the program over to Adam. Show is yours, sir.
All right, I will share mine. All right, you see the screen there? Fine.
Yep, we got you. Thank you.
All right, well, thank you everybody for joining. It's I'm seeing the people on a list. Some of you know, some of the list I don't, but I hope with the question and answer session we get to know each other a little bit better. Joe, thanks for the introduction. We've been a partner with Lyft from 2019 to present. And main reason we have from Loukus Technologies side of things is that there's a common mission in a lot of the different areas. The need for manufacturing to stay here in the US, the need for manufacturing technologies to improve so they can't leave as easily. So with that, we're a small company. We're located in the Upper Peninsula of Michigan. We are separated from the rest of the world by, it seems like 500 miles all the time. So if we were trying to get somewhere, it is typically because we're traveling from the middle of Lake Superior and we're trying to make it to the rest of the world. Little background, Loukus Technologies, while we're a young company, we spun out of another local company here, REL, family-owned company as well, back in 2019. So we took Loukus Technologies' focus and mission is really to develop materials technologies, internal alloy development, process development, and then realize that we are at the end of the world. We'd like to partner with some larger manufacturing, see where we can license some of our technologies and see how we can bring products to market. We're not only interested in doing researchy type things, we're interested in getting products to market, getting products in the military, see where we can use kind of the new combinations of materials and alloy systems that have been developed universities, research institutes around the world, and how can we bring in our background being in building custom equipment and combining that with some materials knowledge, how can we now turn those into real products? So while we're separated from everyone else, being up here, there's an airplane that flies everywhere we want to go. So we've had the opportunity to work with some of the people on this call here in different departments in the military, Army Research Labs, Department of Defense, all over the place, National Science Foundation, Department of Energy through ARPA-E. We've had that unique capability or I guess luxury to get to work with some pretty smart people in some pretty neat places. So once again, a little introduction. Calumet used to be a booming copper mining town. Last year, we just moved into a facility that used to be a copper mine, the engine house of a copper mine. And we're now, we have one of the buildings here. We're going to expand to another for our machining and some of our manufacturing that's expanding right now. So we do get some snow. I always joke with the guys at Lyft when we're meeting that we'll meet them at the border with a dog sled, and they can come the rest of the way that way. But we are in a unique place. We have Michigan Tech University that's 15 miles south of us. So we have a unique set of individuals that from the engineering side that like what the Upper Peninsula of Michigan has to offer, as far as we don't wait in traffic like a lot of different areas in the world have to. So my big complaint of the year was with all the tourists coming to the area, I had to wait for like 30 seconds to get onto US 41, the main highway coming through town. So with that, yeah, we get a little bit of snow, but it does leave for a couple of weeks during the year, which is great. And we're in that time period right now. Giving an overall of what we have as far as capabilities. We're not just a think tank type of place. We have the ability, we have commercial size equipment. We tend to do a lot of R&D here on our squeeze casting presses and low pressure casting presses and building of ceramic preforms for reinforcement and metal matrix composites. And I'll talk a little bit more about the details of each as we go through it. So a bunch of equipment. We have in-house analysis capabilities as far as having an SEM in-house for looking at microstructure. We have the ability to do material testing in-house, as well as work with Michigan Tech on some of the more advanced testing that they have capabilities down on that end. So we have enough equipment to be dangerous. We tend to develop on the front end, but we can not only think of how we're going to combine materials in unique ways. We have the ability in-house to design the tooling, build the tooling, and build the equipment required to make it happen. So that's a quick overview of our facilities. Company history and technologies that we own. Like I say, some of these technologies we developed over the last, I'm going to say since 2006, 2007. But now we brought these technologies in. Each of these kind of gives us a new asset of what materials we can do in-house and how to approach certain problems. There's not one right way to approach a materials or unique materials solution. You know, sometimes it might be casting, you know, and that casting can be gravity casting, low pressure casting, squeeze casting, high pressure die casting. Sometimes it's forging, sometimes it's extrusion. From our perspective, we don't care. I mean, the one thing I'd like to highlight with where I think are slightly unique is that we'd like to see where you can combine some of these casting technologies, some forging, some extrusion, and then combine that with some of the 3D printing, the meld technologies, the wire arc additive manufacturing stuff to see how, you know, how do we bring these products in the best way, right? We have all these unique capabilities, new technologies that are coming out, new alloy systems. We're not tied to, hey, we must squeeze cast because we have squeeze casting equipment here. We don't have to low pressure cast because we have that equipment here. We'd like to see what makes sense and how do we combine each of the attributes of each of these and move those forward. So these snapshot of some of the products you'll see here are combinations and how we approach certain materials and how we develop the product based on that. And I'll give maybe some lessons learned in each of these areas really quickly. Our first product, as we came through and we said, hey, we have some unique capabilities in making, we have some unique capabilities in aluminum and ceramics. Quick story on this is my background is in aluminum metallurgy, aluminum hydroforming. So I did my PhD work in. My brother's was in ceramics machining, that sort of thing. So well, why don't we combine the two of them, make something that makes sense? So a brake application, you know, why not pick the one thing that everyone said couldn't be done, right? Several $1 billion have been spent by some of the smartest people in the world, large companies, large research institutes. And we said, yeah, well, how hard can that be, right? So anyway, we combined the two, making a metal matrix composite. And on paper, it is the best way to approach braking, right? You can be 3 to 4 times longer life than cast iron brakes. You can be less than half the weight. Motorcycle rotor that you see there took out half the weight of a Harley, the brake system of a Harley Davidson. One of the rotors, right upper right corner, I put those on my car and it saved over 40 pounds in a brake system. We developed a whole process for making these things, nearly put the company out of business as we had purchase orders in 2008. Half the bike builders went out of business, and long and short of it, we realized that while you may have a great product and a great material solution, the market also has to be there and waiting and willing to buy your product at the price point that you can make it at. So we learned a bit things on a business side as we developed this product, as well as the technical side of, hey, here's a great product. Is the market ready for it? At the time when we launched this thing, the answer was a resounding no. And it almost put us out of business. As you look at all electric vehicles, influx of hybrids and things like that are in the market, I just truly believe that this technology will have life moving forward. It just wasn't the time and the place when we launched it. Another unique project that we got involved in that we thought, okay, well, we're squeeze casting guys now, right? So we said, well, there was a unique opportunity with ARPA-E launching a product for a non-conformable gas tank for storing high pressure natural gas. Back in 2012, this was an interesting time where the price of gas was similar to what it is now. So there's a big push to look for alternative energy systems for vehicles. Problem with high pressure gas is primarily those are stored in cylindrical tanks. And if you want to use CNG for vehicles, you have another toolbox in the back of your vehicle that takes up all of your bed space. The idea was, can we make a conformable shaped tank that can hold 3,600 PSI? But not only that, from a safety perspective, you got to hold 2.5 times that as a burst pressure. So the tank we developed had to hold 9,100 PSI of gas pressure inside of it. So approaching it from a material standpoint, high strength aluminum alloys, unique processing capabilities, because while you may have high strength at a certain aluminum alloys, they don't necessarily want to flow in the shape that you see on your upper right. So developing different field assisted techniques to try to get that material to form into the shape, have the strength characteristics that we need, design the right geometry, the right flow characteristics, that we have a final tank that will hold pressure, without having, be pressure tight and have the right strength characteristics. So, so this was developed under 3D. We used 3D printed sand molds, primarily in the shape. We stole from nature in this skeletal plate of a sea urchin, developed that into a Schwartz P surface, and 3D printed some sand cores, put this in a low pressure casting machine, added a bunch of field assisted approaches, as in vibration, added power into the melt as it was being formed. And we were able to get a 7075 and A206 to cast in the shapes that people said can't be done. So, but just approaching it from a different approach than what the market said was acceptable. As part of the process where we needed to get metal in places where it typically didn't want to flow due to early freeze off, we developed a insulative casting spray. The texture of this looks like the felt of a pool table if you look at it, how it's sprayed onto a mold. But this was spun out of some work we had done many years ago for NASA, where we developed a patch kit for the space shuttle after the Columbia disaster. So we developed a high aluminum binderless type system, and we then took that technology and said, hey, if it works as a patch kit for the space shuttle, if we now alter it that we can spray it onto a mold, hey, that'll give us the insulative type of properties we're looking for. So runner reduction, scrap reduction, be able to cast metals at lower temperatures than what they can be done. This is a technology we use in-house on a day-to-day basis, kind of our competitive edge. We do sell some of this commercially, but primarily it's allowing us to cast shapes and alloys that typically can't be done elsewhere. Being able to combine the next two slides I'll go through quickly, but being able to combine ceramics in with aluminum gives you an ability to tailor properties that typically wouldn't exist in a typical alloy or in a composite solution that didn't have the metallic side. This is a fifth wheel wear plate. So this sits on the back of a semi where the connecting plate slides in here, and the kingpin from the trailer slides in this point. So the weight of the trailer tongue sits on here. So these are typically greased. Hundreds of thousands of gallons of grease go onto our roadways. This leads to a bit of an environmental issue. For instance, in the state of California, you have to stop, decouple your trailer, wipe the excess grease off of these plates, and recouple before you're able to enter into California with some of these semi trucks. So we said, well, can we build the lubrication right in? So we messed with our MMC composition, added graphite and tungsten disulfide into the mix, and we were able to cut down the wear of these plates and get the lubricity that we needed. I'll talk about the commercial play on both of these things up together. Same thing here. Let's just put diamonds into an MMC. Now, can you cut concrete? Tailoring the material properties where you need it. You have the high thermal conductivity of the hub, similar to what we had on a brake rotor. We have the super wear resistance that you get out of diamond, right? One of the hardest materials known to man. Combine those two together, cast the whole process, and you have a unique product. Both this and the former product, those were some unique products, but the market wasn't quite ready for them, or we as a company weren't quite ready to launch them. So trying to get the right partnerships on both of these fronts is something that's, you know, still in the works. This is something, like say, worked on with having the ability to combine different things. It's obviously great from a warfighter safety type of perspective, right? Is if you can combine some silicon carbide tiles and some of these high strength weaves and some of the lightweight aluminum aspect, it's all very attractive if we're trying to minimize vehicle weight in armor applications. So worked with a few different agencies to try to bring these technologies forward. At the end of the day, cost is still a key attribute. So getting these things all the way through to a vehicle platform is more than just a technical challenge. So getting to, you know, some of the more recent projects we're working on right now. We're working right now on an SBIR project where we are trying to reduce the weight of a mortar base plate. So using some of the combined MMC technologies that we've developed over the past decade, and I can't believe I'm that old to be able to say that, in the last 15 years, we are combining that using like a in situ nano MMC that we developed with some high strength aluminum alloys. And we're able to take these mortar base plates down. An M81 base plate goes from 23 pounds down under 17 pounds. We believe our next rendition would be closer to 15. So not an easy application. They beat the living crap out of these things. It has to take 130,000 pound impulse load when the mortar is shot. And it gets kicked around and buried in the dirt, in addition to taking this punch in the face, you know, at a rate of maybe 3 times a minute. So anyway, that's a project we're working on right now. We've got the first cast prototypes out there. What that forced us to do is say, okay, hey, we needed to work on some optimization. So we upped our finite element analysis game to minimize the stresses in the given high stress areas of these things, being able to put material where we had to be. So obviously some geometric optimization, but also an alloy approach. This project, we worked with EC Industries, another lift member. We worked with them on this and some of their casting and flow modeling design and gating design went a lot into this project. And just from a timing perspective, we went with a gravity cast approach versus likely what this will be in production is low pressure or a squeeze cast approach. What it allowed us to do is to make a thin wall, typically thinner webbed region than what you can form with your typical A206 and 7075 alloys. Got some pretty impressive properties out of them. And these are now, like I say, we did some internal testing and we're actually sending these out and hoping that we get through to a phase 2 SBIR because there's quite a bit of testing that still needs to go through. But I think we're definitely on the right track on this nano MMC approach that we've attacked this with. You know, give you an idea, right? Grain sizes are less than 10 micron. We've got these real tiny particles that are in there, somewhere in the range of like 100 nanometer size. So, but that also just accentuates what is our internal capabilities. Yes, we have a Zeiss Evo 10, similar to what Lyft has in their high bay facility down in Detroit. But just the ability to cast something in the morning and be able to look at it in the afternoon and be casting something else and revising your approach on a materials project is something that it was worth investing in. Even us as a small company, we said this is a key tool for us to have in our at our disposal. So the other part of what makes us a little bit unique is doing some of the testing that we do on the components, building the presses, building the unique setups. We can do that right in house. Whereas, like, say, our background in equipment design and build allows us to look at processes and develop materials and test them to make sure that they're actually going to work when they make it to the field. A unique area that's capturing a lot of attention throughout many different areas is this in situ nano MMC type of approach and things, and having that ability to put different types of develop or form many different types of nano particles inside of aluminum matrices in the initial stage here. Titanium diboride. So there's a common grain refiner in aluminum alloys. We're forming that in situ in small particles. We are also titanium carbide. There's alumina. You can form a bunch of real small particles and melts. And it has some unique properties that are seen in the final MMC. Not all that we can explain right out of the gates, but definitely, like say, in our case, the castability enhancement, reducing hot tearing and some hot tearing prone alloys is something that made it worth pursuing this quite a bit further. Other project work with ARPA-E on was developing a high temperature bushing to replace platinum and rhodium in development of continuous basalt and glass fiber. Give you an idea of why we care about this. The use of composites is growing in the automotive market, military markets, in rebar, so used in concrete applications. The problem is if we just grab one application and said all the continuous fiber that's made in the country right now, and we said, let's just turn all into FRP rebar, fiber reinforced polymer rebar. You could do 11 miles of a freeway with that, 6-lane freeway. So the problem is we don't have enough capabilities in-house, or we don't build enough glass fiber to start with to actually hit all these applications where it makes sense. FRP rebar, the advantage there would be, hey, your roads don't degrade, you don't have rebar that's going to rust and cause cracking. Bridge structures, there's a lot of reasons that FRP rebar has advantages, more than double life of bridges and roads. You can't get there because one of the main hindrances is the investment that you need in platinum and rhodium in just purely in the bushings. To give you an idea what bushing is, it's a plate that has a bunch of holes in it that you have a mass of glass or basalt molten above it, and it has a bunch of holes that it drips through, and you grab that and wind it on a spool, make the toes of fiber, which then get wetted out by the polymers in a subsequent process. Whether it be layup, those get woven into 2D fabrics, for multiple different applications. So we approached this project saying, is there a better way to make a composite bushing that doesn't have platinum at $980 an ounce and rhodium at $25,000 an ounce? Can we approach that with some of our composite technologies that we've developed over the last several years? So that's the way we approach this, is looking at developing an alloy that could handle continuous, essentially be able to withstand temperatures forever. And they don't want to replace these bushings maybe once a year, right? And it has to hold up to 1250 degrees or 1300 degrees Celsius in an oxidizing environment. And it also has to have the right wetting angle so it doesn't wet out by the glass or the basalt fiber that's flowing through it. So this was kind of a set of material challenges. It turned out to be a set of a bit humbling, and understanding how materials interacted, wetting behaviors, and then also being able to tune in a manufacturing process that you could control within a couple degrees to be able to develop a fiber. So By the end of it, this is a 2-year project. The video you see on the right is pulling a single 10 micron diameter strand of glass fiber through our bushing that we developed. A lot of the commercial bushings, there's 4,800 strands of glass, but we just proved, hey, we can do this on a single strand basis. We have the process control to do this. Now it's just the factor of scaling up the bushing technology and building bigger plates, bigger furnaces. So that taught us a few things about how do we have to approach some of these material challenges that are not, break related, which was, okay, 400 degrees Celsius. You can combine aluminum in there. You can have some magnesium applications that are in that range. But now when you jump to 1250 degrees and you need to last forever, your list of candidate materials drops significantly. So you look at a lot of the approaches here where they might be strength, say, okay, well, let's use tungsten carbide. Well, that works great for the hardness, the temperature, if it's in the right environment. So going through a lot of different material selection and down selecting to a final MMC that works was definitely a considerable challenge. So still looking to push this work forward in the coming months. Looking at how we've worked together with Lift in the past few years, there's been some pretty cool projects that not only worked well, I think, for meeting the mission of what Lift was trying to do, but also increased our internal capabilities. One of the ones that's going on is, we developed a rotor in the past. We always looked at how do we optimize the ceramic component of the rotor. And that was our focus as we launched motorcycle brake rotor, launched any type of brake. We tried to pick an aluminum alloy that was available, that was cost effective, and high temperature per se, and hope that was going to be enough. Well, with the advent of many new alloys, aluminum alloys, that eliminate a lot of the lower melting point phases in them and can handle 450 degrees Celsius and then still maintain some hardness, phase stability, these sort of things. We're looking at how do we optimize that aluminum alloy? How do we optimize this metal matrix composite, but keeping it kind of a consistent ceramic sponge on the other side? One of the other projects we worked on with Lift and got the chance to use their high bay space was how do we look at some of the magnesium alloys we're working on for a different project and tailor it for a high ductility application. And we were able to cast several different alloys, extrude it down at Lift's high bay space. We brought our induction unit down as a preheating billet heater prior to extruding. And we got some pretty unique properties to meet the application we were targeting. So this was a successful project, one of the early lift projects that we had. Some of that knowledge all kind of fed into what we do now, right? So in some cases, it makes sense to launch products that are cast or forged, but a lot of times if they need to be forged or extruded, you need a billet to do that. So we have the ability in-house to cast multiple different alloys. We cast different size billets, all the way from 3.5-inch diameter billets that we can extrude at Michigan Tech to 6-inch diameter billets that we extrude down at Lift, and 8, 9, 11-inch billets that we work with different commercial partners to extrude multiple different sizes and shapes of aluminum and magnesium alloys. The other part that we pride ourselves in is maybe we're exuberant on what we think we can or can't do, but some of the custom castings that we work with some partners in vibration fixtures that are used in aerospace structures, putting a certain frequency in, checking mode shapes, seeing how different structures are accelerated. So a lot of things for head expanders and these are a lot of times made out of magnesium alloys. So cast some kind of unique big shapes in those for those applications. So in closing, so we have a few minutes. We've developed and have 13 issued patents where we tend to spend a lot of time in some pretty high markets. And with that, those large markets are not exactly always open to new technologies, new competitors in the market. But the way I think we get around that as a small company is we learn how do we team with some larger partners that are already in that market already, or they're open to some new technologies. Spent a lot of money developing our IP. We spent a lot of money developing our processes and our approaches to these products. And at the end of the day, yeah, some people said, hey, you got something that's worth pursuing. We spent some time developing a patent portfolio that opens the doors to several different markets for us, or helps protect us in several of these different markets that we're addressing. And the idea that, hey, we have a toolbox. We definitely want to see where we can take the conventional manufacturing and add some of the 3D printing aspect. We use some of that internally as part of that process. The X1 sand printers, for instance, for the tanks and some of the castings that we do. But how do we combine that even further, where you'd say low pressure cast one part of the component and then print some of the features on it. And that's a couple of projects we're working in that direction on that. So look forward to working further to, any of you on this call that might be interested in partnering and have some materials, technologies you'd like to focus on. We're definitely interested in doing that. So that's about all from my end, Joe, and I'll definitely open it up to questions that anyone may have. If I didn't, hopefully I didn't bore you to death.
No, great job. Can you go back to the last slide? Because I want to make sure people see your contact information and can reach out to you. Again, if you do have questions, please go ahead and use the Q&A function so we can get those questions answered. So a couple of things that came up. First of all, excellent use of the high bay. Certainly appreciate that, utilizing our equipment that we have here in Detroit on the one project that you mentioned. So a question that I was thinking about as you were going through this, lot of different materials, a lot of different processes, almost like a little bit of everything, jack of all trades type of approach. Is there a specific wheelhouse that you focus on, or is it always kind of growing?
So like I say, we have, like say, if you look at the products that we've been on the front end of developing, the barrier to markets are pretty high, right? So if you look at brakes, that's a multi-billion-dollar market, and it's a very cost competitive market. So we've tried to bring that into an area that is used to, so the drum in this upper corner is, you can buy that $38 out of cast iron from China. A brake rotor for a small car is $14. So we've attacked some markets where we've displayed that technically we can get it done. And I guess we've learned that that's not always enough. You have to have the commercial picture as well. Answer your question, right? We've attacked things being naive, thinking that if we have the best technology solution, people will adopt it. But now we've learned that at sometimes that's not enough, and we need to approach it a little bit differently. So it may appear that we're scattered a little bit, but each time we fail on these commercial side of things, potentially bringing the full picture together, or it's taking longer than we want it to, and we want to just build something and sell it. It's forced us to add another tool in our toolbox, and we approach our next product a little slightly differently. So yeah, if you ask me, it's very much a similar technology approach. Do we combine different manufacturing techniques and technologies together? Yes, but to us, it's kind of all the same, right? Because it's a long stretch between a brake rotor and a high temperature platinum MMC bushing, right? But to us, the actual manufacturing side of it is pretty much a similar backbone.
Right, so for the record, there may be some folks may be having a challenge getting their questions in the Q&A function. So if you want to go ahead and use the chat, go ahead and do that. We can address questions that way. You touched on additive a little bit earlier, but not too much in the presentation. Can you talk about where you're heading with that, if at all, in terms of materials or different processes you're working on that particular process with?
Yeah. So in the past, I mean, it's come a long way too. So for instance, just additive, as a lot of people on this call know, is how do you, at the end of the day, it's great. You can make every different part you ever want to, but how do you make it so that people will actually pay for what you make, right? Mm-hmm. One of the coolest ones I thought that was just like I say, commercially ready was the ability to 3D print sand cores. Mm-hmm. So in this tank you see in the middle of your screen right now, we use the X1 sand printer, and we were able to upload the STL geometry and print out the multiple layers of cores that we could kind of assemble this together. And then we put that sand mold into a low pressure casting machine and then low pressure cast the tank. So that's one. At the time when we did it, it was probably 20 cents a cubic inch. Now with where they've gotten with their technology, I think it's under 10. Mm. Someone correct me if I'm wrong. I thought that's what I just heard from the AFS Casting Congress this year. So, and if you actually own the printers were $2 million back in 2012 when I wanted to buy one. Mm. Now they're closer to 600,000. Right. So all the capital investments there. So that 3D printing technology is now ready that a casting shop can almost justify that, to say, hey, I have a one-off print, or the military has some obsolete parts, but they do still have the model. Yeah. You could send that in. We can 3D print a sand mold. You can be casting it within a couple days and have prototypes out within a week. So that's where that capability allows us to go. The other one from the metal printing side of things is where, like, so we're looking at it for some of the higher temperature applications where metal printing can, they can combine ceramics and metals in some of these powder approaches. So that's where we're looking at, potentially on our bushing, do we build a backbone out of a certain composite and we add the tips out of a different material? So we can print fine features with this, like a printer from, say, Desktop Metals or somebody, right? You can print those features on the face of say a bigger plate that was processed a different way.
And how do you work with different companies and help them? Well, do you work with different companies to help them decide which material or process might be best for their given application? Or provide a different solution for organization like the DoD is looking for something, but they might have different requirements. How do you determine which material, which process is best suited for which application? Do you have that in your wheelhouse as well?
So we try to think that we're not biased towards the different approaches, but I think we tend to be. But as long as you're conscious that you may be biased towards one, it may allow you to say, hey, what's a better way to do this? Right. For instance, we had one approach that was work with a customer, and it had to be cast into billets. It had to be extruded. It had to be made this way. Right. At the end of the day, cost per pound was automatically $10 per pound more than what the competitors would be. The particular alloy system. We approached it and said, well, I think we can, cast that part near net shape. And if we work on our alloy side of things, we can avoid a billet casting cost. We can avoid extrusion cost and a lot of machining cost if we approach it differently. So casting isn't always the answer. Forging isn't always the answer. 3D printing isn't always the answer. So trying to just, if you have enough background in each of them to see what the pros and cons of each are, And then if your customer has an open mind to say, hey, it's, sometimes the best solution is the lightest solution is a steel plate. I mean, to be able to get there I'm obviously a light metals guy, but we're working on a project right now that aluminum and magnesium have no place, and there's no way they'll ever get there. Right. And I'm saying that's the thinking. We can push this wherever. But at the end of the day, it has to be a cost viable solution as well as properties. So
yeah, I guess that was what I expected you to say was as long as you're open to hearing about different possibilities related to the material or related to the process, then who knows what can happen. It could be open to all kinds of developments there. Do you have any advice to particularly our small to medium-sized manufacturers when they're trying to prioritize different ideas as we're getting closer to commercialization? Sounds like you've been on the commercialization side. Where should they put their focus, as they might have some good ideas in terms of which ones should be stacked up?
I see. I have enough. I know how to do it wrong.
All right. So how did you so do the opposite is what you said.
So I like to say, so it's kind of an interesting question, right? So as a small company, limited resources. So it's always a question of, okay, I have this idea, how can we fund it? Yeah. And you go into a big company and I'm just going to I'll put my cynic side of things on. And if you don't have it patented, large companies have a system in place. They can file a patent in 40 minutes. So they don't necessarily want to talk to you if you don't have it patented, but the patenting process alone might cost you $50,000 depending on what you have, right? Yeah, you can get provisionals. Yeah, it's not that much upfront, but that's what you're signing up for when you decide you're going to file a patent.
Right.
So some of the times, we've walked into big companies. I got one example. I gave a presentation in June. By October of that year, they used our images in a patent. Right. My fault. I didn't have it patented. Right. Good luck. Good thing for me. I didn't think it was that great of an idea anyway. But at the end of it, so you're there's this chicken and the egg type of thing where you want to have a certain amount of patents before you talk to your funding agency. And you don't want to do that because there's that capital outlay required to get there. Right. So the other approach is, can you use SBIRs? Can you work with some government agencies that don't want to take your technology, they just want to work with you and get a product? And that's where we found we had the best success with SBIRs. We working with, I think I saw Q on this. I mean, some of the guys at Army Research Lab saw cool technology and, threw a few dollars at it and in some cases lots to develop it for their application. So there's, that's an approach is, okay, how do you work with even organizations like LIFT, right? Some of the LEAP programs, what, formerly was the,
used to be
Fast Forge programs.
Yeah.
You got a cool idea. It meets one of the initiatives you guys got going on down there. That's a great fit, right? The technology is now exposed to a bunch of the commercial players that are involved in LIFT. And that, to me, that's awesome. Because that really quick, you find out, hey, we got how many people are involved with LIFT right now? How many different commercial companies?
Oh man, we've got 300 plus members of the ecosystem around the country. So some are technology and some are talent, but a wide number of them, absolutely.
So it's a great proving ground too, right? If those 300 companies don't care about that, no one reaches out and says, hey, I really like what you're doing here, it's a good proving ground that your idea isn't that good. Right? It may have solved a unique challenge, but nobody sees, and there's a lot of big players that are involved here. Yeah. No one sees where the commercial aspect is or where that's going to fit. You may want to move on.
Yeah. So I definitely appreciate the plug. And it does sound like, protect yourself first as a small manufacturer. the best way possible, whether it's through a patent or working through organizations like ours or through other avenues like the SIBRs and other things that exist out there. Sounds like, and another shameless plug for Lyft. Not only do we have small companies, large companies, project opportunities here, but also have service providers as part of our membership, whether they be legal or IT or other organizations that can work with our membership with kind of working amongst the members to make sure everyone is good to go. And I hope that that continues to be. So we are approaching the top of the hour. And speaking of working on folks working with each other, Adam, if you want to put your contact slide back up there, certainly encourage you to reach out to Adam directly with any additional questions or comments about what he went into today. Questions about Lyft, you can certainly reach out to us directly as well. So appreciate everyone joining us today. Adam, I appreciate the presentation. Appreciate everyone taking the time today. Appreciate your membership, and stay tuned to your emails. And as we continue our Liftoff webinar series, I think we have 3 more in the year 2022 here. So we'll get those out the door. But again, thank you very much for joining today. Hope you have a great rest of the day, and we will catch y'all soon. Thank you, sir.
Thanks, Joe.
All right, talk to you.